Hello, hello. Good afternoon. Good good afternoon. Yes. All right. Hello, Vicky. Hello, Mafine. Hello, Keon. Hello, Victoria. Hello, Bridget. I'm looking at the chat. Good afternoon, Melanie. Good afternoon, Raina. Good afternoon, Roger. Good afternoon, Abid. Hello, Anthony. Good afternoon, Keon for the double. Uh, Good afternoon, Mafine for the double. Good afternoon, Victoria for the double. Good afternoon, Gabriel for the Gabriel. Good afternoon, Vicky for the double. Good wait, sorry, people still coming in. Good afternoon, Caitlin for the double exclamation point. Good afternoon, Andre. Good afternoon, Bridget for the double. Good afternoon, Zoe. Good afternoon, David. Who okay. Oh, and good afternoon, Bridget for the double and Gabriel for the double. Um, And good afternoon, David. Or did I say that? Sorry. Yes. And David. Okay. And hello, Yedaya. For the I know where you live. That's such a weird thing to say. Sorry. Good afternoon, Lear.
Hi,
Yeah.
Professor.
Hello. Hello. Okay. So everybody, so we're gonna start in a second. And we are starting, but I'm a little confused. So I'm looking. It isn't letting you submit. Uh, okay, hold on a second. I'm making sure that we're gonna start and we're gonna start new material in a second, but of course I'm first making sure I'm glad you're all here no matter what. You let me start with that. Even if you're having difficulty or if I'm even if there's something going on with your exam, you're doing the right thing by being here. Thank you. Um, That's definitely part of it, and that's really important. But now, yes, I am looking right now. I see there's some issues with some of the exams. I don't mean I'm not grading. Right now, my concern is just that all the exams are in as they're supposed to be, or that any exam that's not in, there was a prior arrangement. I mean, there were a couple of prior arrangements made. There always are about either, religious observances or medical or stuff like that. And that's fine. If there's a prior arrangement made, then those people know who they are. And I'm glad that they're here right now anyway. But there are some things going on with, bear with me for a minute. This is not, if you turned in your exam and it's in and you know it and I know it, then good. And you should be proud of yourself and you should be breathing out for a moment. So just bear with me for a moment. You're okay if you're okay. But it is an exam. So I want to make sure we're all okay. So hold on a second. Bear with me for a second. And people coming in and out. Oh, uh, okay, wait. So there's actually like a number of things going on in the private chat and some issues with regard to the exam. So yes, some of these things I'll have to deal with after class, but let me just get us all caught up here. Hold on. Bear with me. Oh, wait, and people coming in and out. It's chaos. It's chaos. Well, it's not chaos.
Good morning, Professor.
Good morning. Good to see you. Thank you. Okay. Bear with me for a second. Mohammed and everybody. That's a hand. Sorry, but I'm doing like four things at once because because something's going on with some of these exams, and some of it I can do something about right now, and some of it I can't, or it's not my responsibility to. Um, but I want to do what I can first. So again, just bear with me for a second. Okay, what's going on here? All right. So okay. Wait. Whoa. Uh, okay. Um, so let me put it this way. And I see Melanie, you have your hand up. Give me 1 second. I will totally call on you. But yeah, I mean, exams. So let me just be clear. And this was true in Physics 203 as well. Exams are due right before class. Like homework, well, no, even homework is, right? Like exams are due right before class, and that is kind of important. And then you show up to class, which you guys are doing. So that's good. Exams are due right before class for a variety of reasons. So if, and we're not talking about the exam now. I mean, we're going to move on in a second. Uh, uh, if you're having an issue with your exam, and some of you apparently are, if there's an issue with your exam, you may want to hang out for a couple of minutes right after class and talk to me. The expectation was that it would, and I'm just talking to all of you right now, okay? I mean, obviously there are things in the chat. I'm partly responding to that, but let me say to all of you, yeah, the expectation was that unless we made a separate arrangement, that the exam would be in now. Um, now, and again, I'm making this as a general comment to everybody. In general, the the exams were due now. If an exam in general, if an exam didn't come in now, wait, and there's people coming in. And I know there's a hand up. I will get the hand. I'm just um 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 okay, there are okay. I guess the simplest thing for me to say, so let me just make this clear. I mean, most of the exams are in, that's good, but there are a few that are not. It's slightly surprising to me. And I'm not trying to make a big deal. Let me just say this, okay? And I'm not, and each one of you is a individual person with an individual situation. If you have an individual situation, like we'll talk about it either right after class or later, and we'll find out what's going on. And it may be different from one individual to the next. And okay. So, but what I'm about to make is a broad remark. Um, the broad remark is that the exam was supposed to be in right before class. And for that's good. Well, I was gonna say that's gonna be true for the final exam. That's not, I mean, the final exam, there's no class. So I guess this is the last time this is relevant. Um, and it was also true in physics 203, although not all of you had me for physics 203. So I recognize that as well. It, and take what I'm about to say also as advice for the final exam. I am always open to hearing individual situations and making individual arrangements in advance if there's like medical or religious observance or something like that. For sure, people can reach out to me in advance, and if they need to make a individual arrangement, once I hear it and think about it, I can do that. And I can do that for the final exam. That's part of why I'm saying this right now. Like when it comes to that time. Um, but the assumption is that if I don't make an individual arrangement with one of you, then the exam comes in when it's supposed to come in. If it doesn't, or when it doesn't, and of course this happens from time to time, I'm not saying I'm not going to accept it. I'm not saying that. I'm not saying I'm not going to read it. I'm not saying you're not going to get a grade for it or you're going to get a zero. It's nothing like that. I am saying, just to be clear, that if the exam doesn't come in on time or didn't come in on time, the default assumption is that there will be a point penalty. I'm saying this for the sake of the whole group, particularly for those of you who did make sure to get in it on time. I just want you to know, like, your efforts are being recognized both spiritually and academically. That yes, the default assumption is if either someone's not here right now, if one of your friends isn't here and you're noticing them being conspicuously absent, please know that so am I. I don't often notice on regular days, but on exam days, I'm looking at all this. That's why it's taking me 10 minutes to start the class. I am looking at all this. I want you to know that if you are here and your exams are on time, that's being noticed. If one of your colleagues is not here and I'm looking, and maybe I have a special arrangement with them that you don't know about, that's possible. Or maybe I don't, in which case I want you to know, oh, yes, like that there is a point consequence for that. You should not feel that your efforts were wasted if you got here on time and turned in the exam on time. If your exam's not in, yes, I'm gonna, and I don't, and I didn't have any advanced warning of that, or like or if I didn't have any advanced warning of that, then yes, I would like to speak with whomever you are, like right after class or something, and find out what's going on. Uh, the default is that there has to be some kind of point penalty for that. But it varies on the situation, and I will hear the situations. And no matter what, I'm going to take all the exams. I don't want any of you to worry about that. I will take them all, and I will grade them all. And just depending on the severity or the weirdness of the situation, there will be a correspondingly severe or not severe point penalty. I'm just trying to say this to all of you. So I will hear the individual situations and respond individually, like accordingly. Um, uh, uh, okay. Okay, I'm looking in the chat. So, and if there are situations like, yeah, I'll probably have to hear them right after the class. Um, and I can't hear a million of them, or make an appointment. Yeah. So there's like a number of you in the chat who either you're asking me if you could stay after class for a minute, or I'm asking you. So we will, but there may be so many that we may have to be brief and like make appointments for later, and that's fine. And this is not me yelling. This is me just like trying to be clear and also show like exams are serious. Even if we do them the way that I do them, that sort of makes it all the more necessary to be serious about this moment when we all get together. Okay, so I'm just looking one more time where we are with them. I'm going to move on in a second. I'm just responding to a couple of. Ooh. Uh, okay. I want to move on. My suggestion is this. Oh, and I will get Melanie. I'm sorry. I keep not like forgetting that I am. If you feel that there's any weirdness with your exam, and again, like for example, like it does need to be one file. It can't be 20 separate image files. Like if for example you're putting that there now to show me that you do have an exam, but you recognize and you're trying to be sort of on time, but you recognize that you're going to do something later to fix it. Like, okay, I get that. But I sort of get that. But if there's any weirdness in your mind or my mind, I suggest at least you stay after class, whoever you are, stay after class for at least a minute, at least so we can make an appointment to talk later or something. Uh, because I don't want to surprise anybody with a point penalty. So I'm also just saying it now, like at work, or if you just know in your heart you're late and you're just gonna like walk away and it's just like do it and you don't want to talk about it, I can respect that too. But then but there will be a point penalty like in the absence of discussion. So okay, anyway, I'm just a little surprised because there's more than one that seems to be unresolved. Um, but all right, let me Mel, before I forget, I'm sorry, Melanie, you've had your hand up for a while. I'm sorry. Go.
Hi, Professor. So I noticed that there's two homeworks that's due on the 7th. Is it possible you can push one of them back?
Oh, wait. Okay. Totally legitimate question. Okay. But you're talking about homework, what do you call it? 5A and 5B, right?
Yes.
Okay, so one quick thing about that, totally legitimate question, but those are super optional, even more optional than normal homework. First, so first of all, I'd like you to choose one. Don't do both. That's why they're called A and B and why they're both due the same day. So just quick announcement to everybody, but thank you for reminding me. In terms of that, choose one, don't do them both. And the reason there's a choice or why it's sort of and of all the homeworks, if you were to ever to skip one, you, you could skip that one. And there's certainly, I mean, there never is, but there certainly wouldn't be a penalty if you didn't do homework five. Homework five, whichever one you do, we're not actually going to go over it in class, and it's not literally directly going to be on the final exam. So either one is optional just for points as it is. Okay. And the way to make your choice or the way to think about it is 5A, like it's good material, but it's not going to be on the final exam. We're not going to go over it. But I mean, it's related to stuff we already did. But 5A, you should choose to do if you're planning to take the MCATs, quite frankly. Any of you or that you might take the MCATs or some kind, or even like the GREs or something in some kind of science, if you're going to take a standardized test where there's going to be physics on it, first of all, you should let me know at some point, and I could talk to you about how that goes because it can be jostling at first, but it all works out. Blah blah blah. But if you might be taking the MCATs or something like that for practice and for practice and preparation, I suggest you do homework 5A. If you're not ever probably taking the MCATs or anything, you don't have to do A. Then I'd recommend B. B will help you more directly practice for the material that we're going to do in the rest of the course. But even B won't directly like be on the final exam or something. So either it's an option. That's why they're both due the same day. Choose one or the other, or if you're totally swamped with work from other classes and stuff, you can let them both go and it's fine. But that's the deal with that. Does that make sense, Melanie? Or
Yeah, that makes sense. Thank you.
great, thank you. Okay. Um, right. Oh, a good question. Right. Or someone just put in the chat. Right. If you're an engineering student, yeah, I'd recommend homework 5A. That's another example. I mean, that's not the same thing as taking the MCATs, but right, same category. I mean, same. answer. Do 5A if you're going on in engineering or any kind of like applied science. I think you'll find 5A more interesting, more relevant to your life, and more useful like later on. I guess that's the same thing, but yeah. Good point. Okay. And yes, wait, hold on. I'm just responding to chats. Okay. So I will make more comments about the exam once they're sort of all in, we get this straightened out again. But the main thing, and I'm not trying to be weird. I mean, I'm just trying to be serious. And I'm not trying to freak any of you out. Um, the main speech that I was going to give, or that's a little bit more appropriate later, but the main thing is if your exam is in, great, good job. Like seriously, like whether you found it easy or hard, if you got it in and you're here, you should breathe a sigh of relief. You should congratulate yourself no matter what. And the rest of you, and those of you who are there's a still an unresolved issue, you're going to confront it honestly with me. And I'm going to tell you in advance, honesty will be much more helpful than strategy. Honesty is your best strategy. For when we chat, whether it's right after class or right after class, we make a meeting to talk about it later. Like, and everybody will be okay ultimately. Like the worst thing we're talking about here with some of you is, a matter of how many points. But what I want to, assuming we get this resolved, we're now in the class going to move on to totally different material. It will be intellectually, it should be intellectually a fresh start for some of you because it's like very different. I mean, it's all related, obviously, in the end, but we are going to like start a fresh topic today. That is a fresh start for many of you. I want you to know also, no matter where you were with this midterm exam, it's a midterm exam, it's a checkpoint. I'm a firm believer. Like you have to do it and all of that. I'm a firm believer that the purpose of a midterm exam is to like make sure that when it's done, we all still feel that we have a chance to do well in the course. Maybe for some of us, that means we still have a chance to get an A. Maybe for some of us, maybe it's not about an A anymore. Maybe not. But still, whether it's about a B plus or passing or whatever the standard is, like that is still distinctly possible for everybody. And it's probably still possible to do better in this course than you might be thinking right now. No matter who you are, at the moment that someone works on a midterm or is in the middle of a midterm, is generally when they have the worst feelings about the class and about themselves or about me or whatever. Like that's usually the lowest confidence point is right in the middle of when you're doing a midterm or when you just like turned it in or whatever. So I'm here to say it's important. Usually I give a big speech about this. It's important for us all to know that there's going to be a pause now. Like once you get it into me, it's going to be a little while before you get it back. I apologize in advance. It's going to be longer than you want. I mean, those of you who had me in 203, it won't be as long as that was, but I'm not going to get them back as fast as I would like or as you would like. I will get them back in time for you to get feedback and know what to correct for the final exam. And that is the ultimate point, is for you. In the meantime, until I get them back, know that you're in better shape in the course than you might feel, and that there's still hope. If you feel frustrated by the midterm exam experience in whatever way, I would say you want to double down on like all the game participation point portals and stuff that some of you pay a lot of attention to and some of you pay less attention. It's an opportunity for you to help yourself for the rest of the course. And then obviously we'll talk about the final exam when we get there. But it is still, if you're in the room right now and you're still hanging on and you haven't given up on the class, then the class has not given up on you. That's like my main message to all of you. And I mean, I know I sound a little bit not joyful, but I mean it. Like it is about to be a fresh start. We're going to do material now that you could think about freshly. You could start submitting a lot of point participation portals. You could still do old homework, and you know I'm very behind now in getting back old homeworks to you and stuff. You could still do them. None of those portals are closed, so you should know you have. It's not too late to meet whatever your standard is that you're trying to meet for this class. I think that was the main thing I wanted to say, and but I do mean that. Oh yeah, okay. Oh yeah. So, oh, interesting. Okay, I'm looking. Right. Okay, okay. I'm looking at the direct chat. Yeah, and I mean, we're not gonna have a moment where we like literally walk through the whole thing together. We sort of did that in advance of it. That's not gonna happen. We're moving on in our lives. Um, and nothing that's literally was on that midterm will literally be on the final. So there's no, you know, you can move on in your lives once you turn it in. But yes, to answer a question that's in the thing, right? The exams are lengthy. I made them. The exams are lengthy. I mean, I only asked you to do 2 questions because even that is somewhat lengthy, right? Hopefully that was a relief for some of you, but then also some of you might still have found it was still longer than you expected, as one person said, even with only 2 questions. But yes, to answer your question, when I turn it back to you, it will be with feedback. The whole idea, not just a grade. If I were just doing a grade, I could get it very quickly, pretty quickly. But there will be feedback, and even if I'm still behind on homeworks, the main purpose of these, what I have in my mind when I turn them back to you, is what I need to tell you, each of you, to really focus on for the final exam. That's like the point of it. Now, therefore, you will get it back before you study for the final exam. But the flip side is it's going to take a little longer than I would like or than you would like. Like I'm not going to have a Monday. To be honest, it's just not going to happen. But yes, when you get there, if you're patient with me and if you're patient and understand and tolerant with me, then yes, once you get it back, the main thing that you're going to get on it is what you need to work on for the final exam is this. Okay, that's and that takes me a while. But okay, so will you get it back before break? I mean, that's a good question. Wait, before break, wait, we have this week and then it's break. Uh, I can't promise that you will. I may be using break. You'll, what I think I can hopefully say is that you'll get it by the end of break because I'll use break to, but even I'll be using break to do them again. And I apologize in advance. I'm just trying to manage expectations. You know, I have 4 classes that are this size, and all of the exams are that size. So it's a little bit, and I wasn't able to stagger the due dates, which I should. So I apologize in advance, but it takes me a while. So I probably will use the break to be doing them. So I can't say that you'll get them before break. I apologize, but that's the honest reality of it. Okay. Okay, well that's good. Oh, okay, that's my last thing. Sorry. So someone just said so thank you for your feedback in the direct chat. And I hope, yeah, I'm just trying to be honest. But then someone just said in the thing that they said like it's fine if I don't get it back during break because no one's going to be thinking about grades during break. That's a fair point, a good point, and I want to join you in that. I mean, I wish I could not think about where, but sorry, what I want to say is again, get the exam in if you haven't. Because once the exam's in, then I do want you all to be relieved as you should. Like no matter what I mean, this is a whole long speech that's easier to give once they're all in, but um you should not worry about grades during break. I believe in that. And also, once you get the exam to me, you should congratulate yourself for doing it, for doing your best input, regardless of what the output or the outcome is. There should be a moment between, yay, I did this exam, versus or before, oh my God, what did I get on this exam? Or, oh my God, what did he think about my exam? There should be a gap in between where you're just psyched, it's over, and you don't have to worry about what it means. I really believe that, especially because when you get it back, it's possible you're going to get a number that you're not in love with, but I also want to tell you in advance. And I don't know what that number is. Like, just like right now, I want to congratulate those of you who did it. I'm not looking at the document. I don't know what's in it. I just know you did it, and that is something in and of itself. And it shouldn't be tainted by when it turns out that there are imperfections or incompletenesses in it. It all of this will still, there's still a huge chance that you'll do much better in the overall course, not to mention life, than any one piece of paper seems to suggest. So yes, so don't worry about your grades during break, but I'll worry about your grades during break. Okay. So, all right. So I'm going to shift gears now and deal with new material, if that's okay. Well, I am anyway. So bear with me for a second. Hold on, let me just get my. I'm also questioning whether all that really needed to be in the recording. Well, okay, I guess it is what it is. All right. So here we go. So what we start now is our next, in some ways, our next unthinky thing. The larger topic is electrostatics. We're dealing with electricity, electrostatics from here on in, and related things, electrical charges, electrical forces, electrical currents, magnetic forces. Oh, sorry, I skipped a big one. What we're dealing with from here on in is electrical charges, electrical forces, electrical fields, electrical currents, and related magnetic forces and fields. Ultimately, the goal is to be able to say something about what it means to put all that knowledge together and understand something about electromagnetic radiation, which is to say light. But so we're about to enter into that whole realm, like right now. And the main goal of today in the next 41 minutes is for me to establish the meaning and application of this equation on the board, which I mean to be new. And I see there's something in the chat. I'll get to the chat in 1 second. This equation is a goal. I'm not claiming that you've seen it before in this class. I'm saying I'm going to develop it today. I'm going to give you some other equations too along the way to this, but this is the goal. This is Coulomb's law for the electrostatic force between two charges. I will say that again more in a couple of minutes, but just so you know, so that's where we're heading today. And I can't remember if you've already looked at some of this in the lab. I don't think you have, but we're about to get into the electrostatic force that one charge exerts on another. That's where the ship is heading. And I'm going to get there in a minute, but there's more in the chat. 1 second. Oh, cool. Okay, good. Thank you. Okay. Now, again, also, that's my goal. Sorry, as far as the exams back, so I'm just seeing things in the chat. That's what I'm going to try to get them back by after break. Even that, I mean, I'm not putting that, I'm not like writing that as a blood oath, but that's the idea. Yes. But what is a blood oath is that you will have them back in time to know what to do for the final. Like that's the blood oath. That's the final rule that I can't violate in my own mind. Okay. All right. So this. So let me back up. So this is electrostatics, but the way to understand electrostatics is to first either remind yourself or for the first time think about how gravity works. Like the ultimate claim I'm going to make is that the way one charge interacts with another charge is mathematically identical to the way one mass interacts with another mass. The way one mass interacts with another mass in the universe is called gravitation. So let's first take a look at that. Okay. So I'm explaining the law of universal gravitation to you. And for some of you, this is like a reminder or like a review of old concepts, and to some of you, it's new. But I'm going to say it from the beginning. So assume you have two arbitrary point masses somewhere, anywhere in a lab or anywhere in the universe. Like you have a dot of a certain amount of kilograms, and you have another dot of a different amount of kilograms. So one dot is like denser than the other. So they're particles, they're point masses. Um, Finite amount of mass shrunk into an infinitesimal amount of volume. So So assume that capital M1 stands for the bigger of the two masses, and lowercase m2 stands for the smaller of the two masses. And then assume that they are a displacement of r away from each other. So displacement is a vector, right? Displacement means distance and direction. So assume that there is a displacement vector that whose length is the distance between the two objects, and whose direction points from the bigger object to the smaller object, like just by convention. Okay. Then I think you'll recall from when we talked about now this is where we're going to start to use some of the math that we never did yet use from homework 2 from math methods. Remember when we were talking about dot product and cross product and stuff like that? We established this idea of unit vectors. Like, remember that if I say there's a displacement vector of r, then a way to understand that is that r is really a simple product of a raw magnitude with a thing with a raw direction known as a unit vector. Stop me if you, but we discussed this unit vector business, a while ago. In other words, it's a little bit circular, but a unit vector by definition is some vector divided by its own length, right? So the unit vector for r is a vector that by definition points in the same direction as r, but has length of one unit, in this case, 1 meter, right? And that enables us to think of the vector r as the way we think of the vector r is we think of a unit vector pointing in a certain direction, and then we scale it up by the amount of lowercase r without any symbol over it, right? I mean, this is technically a review, but in other words, if r is 5 miles pointing to the northeast, then how we think of it is that we originally have some unit vector r hat, some vector that is 1 mile pointing to the northeast, and then we multiply that by 5. We scale it up by 5 to get a total of 5 miles pointing to the northeast. Like that, okay? So I'm just reminding you that for any vector r, there is a corresponding unit vector that points in the same direction. All right, so this is the situation. We've got point mass 1 and then point mass 2, and the displacement r points directly from point mass 1 to point mass 2. Well, then if we have that situation, so this could be any 2 point masses in the world, then according to Newton, Okay. According to Newton, mass 1 will automatically exert a force onto mass 2, a force that is a vector. I mean, all forces are vectors. So mass 1 will exert a force vector onto mass 2 that is given by this equation that I just wrote here, and has therefore a direction and a magnitude according to this equation. So let me break down this equation for you, what it's saying. But whatever it's saying that any mass 1 that you ever could consider and any mass 2 that you're considering will obey this law. So any object mass 1 will automatically will automatically interact with any other object according to this law. And since this law is about forces and all forces obey all of Newton's other laws, then this force will obey Newton's third law as well. So anything I'm saying, I'm about to say what M1 does to M2. But according to Newton's third law and according to like how multiplication works, I mean, it's commutative, then anything I'm about to say about what M1 does to M2, it's also true in reverse, that M2 would do it to M1. But what am I about to say? Okay. First of all, let's deal with direction. That unit, like it says, F equals negative blah times R hat. Now, remember what I said a minute ago, the way we think about, and so F is a vector. It's a force vector. It's a vector that has magnitude and direction. The magnitude is everything inside that parentheses. The direction is R hat. So what that means is, like I said before, the way we think about vectors is we think of them as like unit vectors that are then scaled up or scaled down by a certain amount. So R hat, so we think, okay, if M1 is over here and M2 is over there, in our minds, we picture a unit vector, R hat, that points in the same direction as R, that points from M1 to M2, but by definition has a length of 1 meter, right? So we picture this little unit vector over there. And then we're going to scale up or scale down this unit vector by a certain amount. Well, what amount? Well, inside the parentheses, you see M1, M2 over R squared. So first of all, what it's saying is take the mass of the first object, multiply it by the mass of the second object, divide by the square of the distance between them, right? Like the R that is in the denominator. It's not R vector. It's not R hat. It's R. What is R? R is the pure magnitude. Like when R doesn't have a symbol above it, that means it's the pure magnitude of the vector R. So if the entire vector R is the displacement R, then R without a symbol above it is the magnitude of displacement known as distance, right? I mean, I'm being very technical here, but the R in the denominator is a number, like how far apart these two objects are. It's just a pure number of meters, and we're supposed to square it, put it in the denominator, and we're ultimately saying that we're going to get some scaling factor here. We're going to get a magnitude of force that is directly proportional to how big one of the masses is, directly proportional to how big the other mass is, how heavy, and inversely proportional to the square of the distance between them. Now, that sounds obscure and unusual, like inversely proportional to square of distance. It is unusual at this point. We've never seen it before, but it's evidently the case. It evidently works, and there are reasons that we're going to get into as to why it works, why it's true. But the first thing I'm saying is, okay, this scaling factor, the magnitude of the force is directly proportional to M. M1 directly proportional to M2, inversely proportional to the square of the distance between the two. So in other words, if either one is heavier or both are heavy, they're going to pull or they're going to interact with each other with a stronger force. And then if they're closer together, they're going to interact with each other with a stronger force. But then there's this capital G letter in the parentheses. There's this capital G, which is a constant of proportionality, literally a constant of proportionality. It's so constant that it's universally constant. It is a number that is true throughout all of space and presumably all of time of the universe. It happens to be this teeny number, 6.6, approximately 6.67 times 10 to the negative 11th newtons meters squared divided by kilograms squared. Now, I'm not saying you have to memorize this number, but you should be familiar with it. And you should notice a couple of things. So this number is a constant of proportionality. It's saying first multiply by the mass, by one mass, multiply by the other mass, divide by the distance squared, and then multiply the whole package always, in every single case, by this number, 6.67 times 10 to the negative 11th. Couple things to notice about it. One, it's tiny. That's important. All other things being equal, the gravitational force that one object exerts on another object is in and of all other things being equal, it's a very small force in magnitude. Things have to start getting very heavy. The masses have to start getting very big to overwhelm this number 10 to the negative 11 and start making like any noticeable difference in the world or start being bigger compared to other forces that exist in the world that we'll get to. So first of all, it's very small. Second of all, the units of this number may seem obscure or even intimidating at first. Newtons meters squared divided by kilograms squared, like what the what? But the units actually give away the whole deal of this number. If you look at those units, newtons meters squared divided by kilograms squared, they are just the units needed to cancel out the kilograms from the numerator, to cancel out the units of M1 and M2, and then cancel out the meters squared from the denominator and be left with just pure newtons, which is what any force in the metric system should be measured is in newtons. So really this crazy number, 6.67 times 10 to the negative, that's just a constant of proportionality that we stick in, that we need to stick in, that turns out to be the right scaling factor or conversion factor, as long as we're trying to stay in the metric system and measure a force that is measure a force that is properly registering as newtons. Okay, so in other words, one of the reasons you don't have to memorize this number or think it's magical or it's super important, but it's not magical or anything like that, because if we were measuring in feet and pounds or something like that, and inches rather than meters, kilograms, and seconds, then it would be a different number. It's just a conversion factor that makes sure everything cancels out properly and gets us to newtons. Okay. So it's a constant of proportionality from now on that just makes the units work out. So what I'm saying so far, and then I will move on in a couple of minutes, what I'm saying is the first thing you do when you're picturing the gravitational force that one object exerts on another, first in your mind's eye, you draw a unit vector, r hat. Then you scale that unit vector down by a huge amount, and the scaling factor includes these units in it, so that you're now changing that number 1 to some other teeny tiny number, and you're changing the meters to newtons. So you end up getting a vector that's teeny tiny compared to that, a vector that will represent F, the force that M1 will exert on M2. But before I draw it, or before we land the plane, you notice that there's a negative sign out in front of the whole thing. So that negative sign means the last thing we do before we draw this vector or picture this vector is that we flip it, excuse me, 180 degrees. Right? I mean, we change the direction of it so that it's the opposite of what it was. So that if originally R hat pointed in the same direction as R, which is by definition or by convention from M1 to M2, if we're looking at the force that M1 is exerting onto M2, then at the last minute, we start with this R hat vector, we scale it down, and then we flip it to make the force vector. So the force vector will go like this, will go the other way, and will be very small. We get a final force vector, F, that points in the opposite direction and is very small. And what does that mean? And so the direction of F is toward M1. And the magnitude of F is GMM over R squared. Notice also the magnitude, let me say that again. The magnitude of this force vector is GMM over R squared. You don't then multiply by anything else, like the R hat that's at the end of the whole thing. Remember, that has a magnitude of 1. So it doesn't, and that's the whole point. It doesn't change any of your multiplication or anything like that. It's there to say direction. So you start with a direction that's going that way, and then you scale down the whole thing, and then you flip it. And why? Why all this flipping and everything? Because at the end of the day, the force, where do I want to write this? The force at the end of the day, because we flipped the vector, the force that M1 exerts on M2 points toward M1 because of that negative sign. We flip the vector. So the force exerted by M1 on M2 points toward M1. And what does that mean? It means that M1 is pulling M2 toward it. It means attraction. And gravity, of course, as you know, but now I'm trying to show you mathematically, gravity is always has that negative. If you write it as a vector, it always has that negative sign in it. It's always the negative of R hat, which means that negative sign means that gravity is always a pull, or i.e. attraction. Negative of R hat means it's attraction, is what I'm saying. Okay. Sorry. So what I hopefully just did there, I'm going to move on in a second. Okay, well, here, a couple of comments. Let me read this and summarize what I'm writing here. So I'm setting this up, this gravity thing, to make a compare and contrast to electricity, like which is really our focus from here on in. But so I want to make some comments about how gravity works, but just so big picture of what I just did. Like again, hopefully some of it was like old news to you, but then some of it might have gotten like annoyingly technical. The big picture I'm just trying to say is that for any one object that's sitting around, it will automatically and necessarily pull on any and every other object that's sitting around. Like any bit of mass, every bit of mass anywhere in the universe will automatically pull on any and every other bit of mass in the universe. It'll exert a force vector that pulls the other mass to it. And the amount, it's always a pull, it's always toward the thing that's pulling. That's what pull means by definition. And it's always by an amount that is determined by how heavy each of the masses are and how far apart they are from each other. The heavier either one is, the stronger the pull, the closer together, the stronger the pull. Okay. So in some sense, that's all I'm trying to say. And I think you kind of like know that, or I think you can handle that. But then I'm trying to show you how if you write the force as a vector, if you're careful about writing it as a vector, then the way to do that is to employ unit vector notation and a negative sign, and that captures rigorously the idea that the direction of the force that the center of the sun exerts on the center of the earth, that the direction of that force is directly along a line connecting the sun to the earth, along that line but pointing toward the sun. Like that's how we're thinking about it. So all the technical stuff I just said is like how to picture a unit vector and then scale it up and flip it, scale it down and flip it to make the force vector. Okay, okay, now what to take away from that is, first of all, the gravitational force is just a force. I mean, it's not just, but it is, well, it is just a force, like the friction force or like the normal force or like springs, like the elastic Hooke's law force. It's a force. Force always means an interaction between two objects. Any kind of force in physics is always a push or a pull that one object exerts on another object. Like always. Gravity's not an exception to that. It is just one of those. Furthermore, it obeys all the rest of Newton's laws. I'm going out of order. Sorry. Furthermore, it's a vector. Like forces have magnitude and direction. Always. The friction force, the tension force, the spring force. They're always vector quantities. This is no exception. Furthermore, like all other forces, it obeys Newton's laws regarding forces. So first of all, so it obeys Newton's third law. It's a reciprocal symmetric interaction between two objects. Anything I say about M1 pulls M2 toward it, it's also true at the same time that M2 would pull M1 toward it in the exact same strength, I mean, with the exact same number of newtons, but in the opposite direction. Okay, so no exception there. And it obeys Newton's second law, which means it's a law of gravitation is a force that, like many other forces, can be plugged into the left side of F net equals ma and ultimately contribute to acceleration of an object, right? Now, like all forces, just because gravity is acting on an object doesn't mean gravity is the only force acting on an object. It means it's a contribution, maybe a very important one, to the sum of all forces that yield acceleration of that object. All right. So I'm just saying it. So it doesn't equal ma by itself. It plus whatever other forces are acting on an object equals ma. So in all of those senses, gravity is just like another force that we're just now going to study in detail, or that we could study in detail, but instead we're going to study something like it called electricity. However, before I go any further, the reason that I'm focusing my attention on gravity before moving to electricity, to the electrostatic force, is that Gravity is a force, but it happens to be one known as a fundamental force, just like the one that we're about to study. It's a fundamental force that is illegible. What do I mean by that? When I call something a fundamental force, like unlike tension or normal or friction, a fundamental force means a force that acts, that kicks into being just as long as the relevant objects are existing. Like M1 does not have to do anything at all to M, it doesn't have to be doing anything special in order to pull on M2. Gravity is universal in that the minute you have a mass somewhere and you have a mass somewhere else, they will pull on each other automatically just because they exist. Like evident, which is kind of crazy, but apparently true. I shouldn't say it's crazy, but it's kind of unexpected, but it's apparently true. Um, you don't have to be doing anything to exert a gravitational force. More, you don't have to be velocitizing in any particular way, for example, but even more particularly, you don't have to be touching M2 to exert a gravitational force on M2. Gravity works at acts in a manner that we call action at a distance. M1 can be separated by empty space from M2, and somehow M1 will still pull on M2. Like the sun is not touching the earth, and it somehow still seems to pull on it, according to GMM over R squared. Furthermore, you could put stuff in between the earth and the sun. Like you could put Mercury in between, and that won't block the force. So the force somehow just acts through empty space or through matter. Either way, it doesn't require any physical contact or material medium to transmit this force. That's what we mean by a fundamental force. Furthermore, I want you to notice that this fundamental force, I mean, it totally can act, through empty space. It can act through any amount of empty space you choose, but somehow it does matter how much the empty space is. Like the bigger the empty space, the weaker the force, inversely proportional to the square of the distance. It has that property that it's certainly taking into account the distance between two objects, and it's specifically taking into account in this inverse R squared way. Those are my comments on gravity. Now, everything that I just nailed down about gravity, I want you to bear in mind, because now we're going to say with 9 minutes left. So this is from Newton from around the turn, like Newton died in 1727. This work is like from the late 1690s or early 1700s, and we know it from there. Then we come to like the late 1700s or maybe even like the early 1800s, and we have a new, the discovery of a new fundamental force or fundamental interaction. We have Coulomb's law. Here, we're not talking about 2-point masses. We're now talking about 2-point charges, like proton and an electron, something like that. So according to Coulomb, if you have 2-point charges, two really small pieces of material that happen to be charged, like a proton and an electron, or a proton shrunk down to the size of an electron and an electron, or something like that, or two electrons even, then according to Coulomb, one charge will exert a force vector on the other charge according to this equation, which is, I hope you see, the exact same mathematical form as gravitation. And this too is fundamental. So this too is a force that exists just automatically, that just as long as the two objects of this type exist, they will interact with each other according to this equation. There could be empty space between them or matter between them. It'll still happen. And it's an inverse R squared law, just like the other one. Now, why are fundamental forces tend to be inverse R squared? Is it a coincidence? I think not. But for the moment, I mean, as we're discovering them and as they were discovered, it looks that way. I mean, it's just like an interesting thing to notice. We will get into the reasons as we figure them out, just like they figured them out, but not yet. But let me, if we were to end right, we have 5 minutes, but if we were to have to end right now, or you were to go, the main takeaway I want to say, first of all, is that the way a proton pulls on an electron, or the way that a proton pushes on another proton, is exactly mathematically the same way that a mass pulls on another mass. That's the big takeaway here. The vectors and everything work the same, we just have to make some adjustments. First of all, first of all, the constant is now different. It's functioning the same way, but it's a different constant. It's 8.99 times 10 to the ninth newtons meter squared over Coulomb squared. Okay, so first of all, it's a very big number now. This is called the Coulomb constant. It's functioning the same way as the G of the other, making the units work out and all that, but it happens to be a very big number, number one. Number two, it's not making kilograms cancel out anymore. It's making something called coulombs cancel out. Coulomb is the SI unit for electrical charge. So let's get perspective on that very quickly with 4 minutes left. Like, so Coulomb is the SI unit for charge. To get perspective on what that means, one proton has a charge of approximately 1.60 times 10 to the negative 19th coulombs. One electron has a charge of negative 1.60 times 10 to the negative 19th coulombs. This is like from the milk and oil drop experiments. It's pretty big, amazing that anyway, that's a charge. Charges, electrons and protons, as you know from chemistry, are like the fundamental packet of charge. They are objects. They are thingy things. Protons, they're very small, but they are thingy things. So they also do have mass. Protons and electrons interact through electricity, but they also interact through gravity, just a much smaller amount. So just for perspective, the mass of 1 kilogram is approximately 9.11 times 10 to the negative 31 kilograms. So it's a lot less. Well, anyway, it's very small. And the mass of a proton is not the same. It's approximately, I always get this wrong. I always get this wrong. I always get this wrong. I think it's this. You can check me on that, but I think that's right. It's like, 1,000 times bigger than an electron, but still very small. Right. So a coulomb, we have 2 minutes left. A coulomb, in other words, a coulomb is actually a large amount of charge. Like like one proton has a very small number of coulombs of charge, 1.609 10 to the negative 19th coulomb. In other words, what is a coulomb? If from now on I say a coulomb of point charge, I mean you should picture like 16 quintillion protons jammed together in a tiny space. 16 quintillion protons would be like a coulomb of charge. So that's not that so that's a lot. That's not crazy. It's not like impossible to have 16. I mean, their protons are very small, but that is a lot of charge. Or put another way, the proton has a small amount of charge when measured in coulombs. But coulombs are the fundamental unit. Why? Because we discovered we were playing with electricity through wires, macroscopic amounts of current way before we actually broke down and discovered like the building blocks. So it's all scaled kind of in a funny way, but that's the deal. Last thing, we have 1 minute. Last thing. There's this number you need to know, or you need to know about. There's this thing called the permittivity of free space. And I'm saying this very quickly, then we're done. All you need to know about it is that K number functions just like the G number, but usually often I won't write it that way. Often, sorry, we will write it this way. We won't write it as one big number K. We'll write it as 1 over 4 pi times this crazy small number for reasons I'll get into. But just so you know, you could write the equation this way with a K in it, or the more proper way that's ultimately more convenient is the way I wrote on the first page. Instead of writing K, you just substitute this 1 over 4 times pi times this other small number. It works out to be the exact same thing, but it's a more convenient way to write it for reasons I'll get into, but that's the class. So thank you for being very patient. Congratulations again. I'm going to turn off the recording. Hang out for a second if you need to talk. Well, either one is, well, ultimately this way is better. You need to know both. You can write it either way whenever you have a choice, but ultimately you need to be able to read both. This is better, honestly, the way that I've written here, but we sort of build to it from the other one. But I could say more about that later, but good question. So I'm turning off the recording.